And I'm going to go and share my screen. Okay, everyone, it's 9:30. Glad to see you guys. I missed you on Thursday. I hope distributed loads went well. I'm really excited because today we're doing full-scale statics with everything. So just to remind you, we're putting everything together now. You learned about components, how to check them. You learned how to calculate resultants. You learned how to set up statics problems, and you learned how to solve static of particle problems. We learned about pulleys, and then we moved into moments, 2D, 3D, vectorially, right-hand rule. We did moments about a line. We learned about couples, equivalent systems. We learned about all those connections and the reactions at the supports. Remember, the word connections and supports are synonymous. They're the thing that connects things together. And we found out what the reactions and supports. And then the last thing we did was distributed loads. So now we are on the module called Tuesday, Thursday, October 20th and 22nd. We're doing 2 and 3D statics problems. Today we'll do 2D, and then you'll have your quiz. And then on Thursday we'll do 3D. And basically now we're doing full statics problems. At times you'll be drawing free body diagrams of particles, and at times you'll be drawing free body diagrams of rigid bodies. So just as we did in the past, we had setup. And here are all the steps, you guys. Here are all the steps in solving these problems. So let's take a look at what the steps are. And you're very familiar with them. And then we're going to go through 2 problems. So whether we're working with concurrent forces or non-concurrent forces, we're looking at the same steps. Given and find, you write down for given the sketch information and any information that's in the description that's not in the figure, and then what your unknowns are. And then tables, we're going to do the table again. But now notice, instead of just identifying forces, we're also identifying moments, because there are moments in our system now, okay, concentrated moments. And then we figure out the unknowns, the number of equations. So now, Amani, I'm going to start with you because I know you're here. So now in 2-dimensional problems, well, let's say, in statics of particles problems for 2D, we only had 2 equations, some of the forces in the X and some of the forces in the Y. But in 2D problems now, in complete statics problems, we have 3 equations. What's that third equation, Amani?
The sum of the moments?
Yeah, sum of the moments about what axis if it's 2D?
The z-axis.
Z-axis. So now you'll notice for 2D problems, there are 3 equations available. Some of the forces in the X equals 0, some of the forces in the Y equals 0, some of the moments in the Z equals 0. So that means for every 2D body we draw now, we could have 3 unknowns. We could solve for 3 unknowns. Angel, you here? I can't see all the names.
Yes.
Okay, Angel, for a 3D problem, this makes sense? Now for a 3D problem, we have 6 equations that are possible.
Yes.
Yeah, because now we have some of the forces in the X, Y, or Z, and the sum of the moments in the X, Y, or Z. So in a concurrent, going back, bond, and when we had forces that are only concurrent, and we had a statics of particles problem, how many unknowns could we solve for in 2D before?
Would it be 4? I meant 3, because X, Y, and
Wait.
the moment Z.
In statics of particles problem for 2D, we only had 2 equations, some of the forces in the X and some of the forces in the Y. So we could only find how many unknowns?
Just 2.
2. But if we're dealing with a rigid body, we actually have a third equation, so we could have 3 unknowns. And Colin, are you here? Okay, Daniel C. For a concurrent statics of particle problem where all the forces were acting on the same point, how many equations did we have when it was in 3D?
Wasn't it just 3?
3. Some of the forces in the X equals 0, Y, and Z. But now with these rigid bodies, we actually have 6 equations. So we can find 6 unknowns. And then we figure out which body to analyze. We draw the free body diagrams. We do the components and the checks. And then we do our equilibrium equations. And we're going to solve the equilibrium equations in the most efficient way. Okay, most efficient way. So I'll leave the steps up here just as a reminder. Can you see it? How come I can't? Okay, good. So I'm going to leave the steps up here, but we're going to do a problem now. So you guys, actually, I am going to take it off so I could see everybody. Okay. Hey, everybody who joined us. So we are doing full-blown statics problems now with moments and forces. We're putting everything together. We already know it is totally effing awesome. Okay. This is the first problem. So we're doing 2D problems today, and then you'll have time for the quiz. So this is the first problem. Hopefully you could see it. It says a structural member, which is this thing like a sideways T, is loaded and supported as shown in the figure. Determine the reactions that support A and B. So I'm going to get my engineering paper out. And hopefully you could see the picture somewhat. But we're going to go through starting the problem. So Daniel Hall, are you here? Yeah, you are. Daniel, what's the first thing we do in these statics problems? Okay, we're going to Danny.
Yes, we do given and find.
Given, right. And for given, what's the first thing we write?
The sketch.
Right, sketch info. Can everybody see what I'm writing, or is it too small?
No, it looks good to me.
Yeah, that looks good.
Okay. All right, is there anything, Danny, keep going. Is there anything in the words that's not given in the pictures?
No, nothing from the words.
Okay, so the next thing I do, Danny, is find,
Yeah.
right?
Yeah.
Okay. So what do they want us to find? Take a look at the picture. It's asking for the reactions that support A and B. And you guys remember, we want to make sure that once we choose a variable, we always use that same variable throughout. So let's do it in the find. They want to know reactions at A and B. So Danny, what support is at A?
That is a pin.
Right. And up, no questions. It's a pin.
Sorry, it's a pin. Yeah.
Okay. And what are the reactions at a pin?
It only has two reactions.
Right. Which are?
In the X and the Y.
Right. Okay. And it's at point A. So what do you want to call those guys?
F of A, or no? Well, F of
Let's
A.
call it AX and AY.
That's better.
Let's get rid of the F's because we don't want to curse. And we're going to do some of the forces in the X. So we're going to use an F sometime anyway. So let's try to stay away from F's.
Okay.
Okay. And if I want to call this scrap, which I know a lot of you guys like to do that, put the AX there and the AY. And Danny, one more thing. What's the reaction at B? What kind of support is that?
It's a ball.
It's a ball or a roller or something. What's the support that it has?
It only has a reaction in the X direction.
Which direction?
X direction?
Which direction?
Yeah, the X.
No, Y. Not WHY, it's the Y. Look at this.
confidence,
It's
though.
really just a normal. This whole thing, this whole frame here is connected here at the pin and it rests on this. So it's really just a normal.
Okay.
I probably would call it a normal because I know which way it's going to go. It's going to go up, right? But if you want to call it NB, you can. You could call it BY if you want. But I suggest that whenever you can, use an N for normal, use a T for tension, and use W for weight. So be consistent. So let's put NB, although we just had to put N. Okay, so first we did the given and find. We're up to Dave now. Dave, what's next?
Let's see.
So go back to the steps.
Yeah, we're going to make our table. We're going to make
Table.
a table of forces, and now we're also going to include reactions on our table.
Correct. And now you guys look at this. Notice my first column was used to be forces, but it's forces and moments now, because there might be some concentrated moments. Magnitude, direction. So Dave, what are the forces that are present?
We have the 200 and 300, which should we make it to a couple with 200s? or no?
Ah, great. Good. We're thinking about couples. I was thinking we were going to get to Jordan at this point because she's the one who always recognizes it. Certainly, they're couples. There's what couple do you see here?
Right. So do we want to say 200 positive x, 200 negative x?
Sure.
And then there's
And you could make it a couple, you could leave it alone. In this problem, it's not really that complicated. So you could leave it alone, but what do you guys want to do? Dave, it's your choice because we're up to you.
well, you already wrote them out, so let's leave them separate.
Leave them separate,
So-
okay.
We've got 200 positive x, 300 negative x, 100 negative y. We've also got all the reactions, so we need to put a, x, a, y, and b.
Right. And what do we know about those magnitudes?
I don't think we know any of the magnitudes,
No,
but
we
we
do
know
not know
all
any.
three directions.
But we do know the direction. So in the end, how many unknowns do I have?
There's 3.
3 unknowns. How many equations do I need?
We will need 3.
And is a 2D a 3D body?
It's a 2D body, but now that gives us 3 equations.
Right. So how many bodies do I need?
We need 1.
Great. And what body do you want it to be, Dave?
The bracket,
Yes.
the cross-shaped metal.
Great. Okay. Now you guys, I was looking at your, I graded your equivalent system homework yesterday, and you guys are getting sloppy on rigid body drawings. You have to draw the whole body. Okay. So what do we have here? This is
As
point
opposed to
A.
a particle?
What?
As opposed to a particle or as opposed
Well,
to,
let me go ahead. I mean, when you have a rigid body and you have a beam or this, well, let me go there and then I'll clarify what I mean. Here's A, here's B. I have 200 pounds. I have 100 pounds. I have 300 pounds. Okay,
Joanne, I have a question before
Yes.
we move forward,
yeah,
because this kind of threw me on on the free body diagram homework.
okay,
Force, the 100-pound force that goes down,
yes,
that causes a moment
correct.
around A or B.
Yes.
Where is that included? Is it,
Okay.
because so far we haven't said it.
Right. So, really good question. Everybody hear that? This 100-pound force creates a moment on this bracket. Where do we draw it? We don't draw it because a moment is not being applied. It's a force that's being applied, but the connections are going to experience that moment, possibly. Or these connections, in this case, we don't have a fixed connection, right? So there are only forces on these 3 connections. It could be that if the 100 is creating a moment here, there could be another force on the other end counteracting that moment. So you only draw what was applied. Like if I put a screwdriver into here, there would be a concentrated moment and I would have to draw that moment. And the next 2D problem, we're going to have a situation like that. But here, forces can balance each other out, right? Just like on a seesaw, if you were sitting on a seesaw and a kid who's lighter than you moves in and you move out, you're both applying weights, but you are creating a moment, but you could be balanced out and then there's no moment created because one force is creating the moment in this direction and the other force is creating that moment in the other direction. Did everybody
Okay.
understand that seesaw example? Here, I have a pen. Here's the pivot point. If you at 150 pounds sit here, right? And there's a kid that you want to do it with who only weighs 50 pounds, you're going to have to move that kid 2/3 in. And then your weight, the other way around. You have to move in 2/3 in at 150, and you have to put that kid all the way on the tip. So you put the kid on the tip, he weighs 50 pounds, you weigh 150. So the moment created at the pivot point is 150 times the 1/3 distance going this way, rotating this way. But the kid at 3 times the distance is creating a moment going in that direction, and they balance each other out. So that's all that was here were 2 forces that were applied. I never draw the moment, but I could calculate the moment. It's the same in this problem. I have forces being applied in all directions, and these forces are going to counter out the moments that are created by this 100-pound force. Does that make
Okay.
sense, Dave?
Yeah, thanks. I think what's tripping me up is we know that it's static, because in my head it's like, well, it could be twisting it, but we know it's not. We know it is balanced out.
Right.
Okay.
Correct. That when you look at the problem, you could see the 200, the 100, and the 300, they're all trying to twist this, right? They're all trying to twist this T. But these 2 connections are preventing that twist from happening.
Got it.
Okay, so let's look at free body diagrams. There are 2 important things that are not on this free body diagram. So what is missing? Oh, I'm up to David. David?
The x-axis.
The axes. So we could draw it off to the side if we want, if we don't want to complicate the problem. What else? It might be hard to tell, David, but if you started doing your equations, what is this drawing missing? Let's say you want to do a sum of the moment equation. What would you need that you don't have?
I'm not sure.
Well, think about it. If I wanted to find the sum of the moments about A, it would be 100 times its distance, but it's missing all the distances,
Oh yeah.
right?
Yes. Yeah.
Okay, so let's put the distances in. This is 2 feet, 4 feet, 3 feet, 2 feet, 2 feet. So what did I mean earlier when I said you guys are getting sloppy? Is that you want to make sure, let's see if I could, here's my beam. On the beam or the bracket, I labeled the points, right? I showed the forces with the arrows, and I put in the distances, and I put in the axes rather. Make sure that you're putting in on the distances. Don't draw some sloppy crap for me. Draw a nice free body diagram. Doesn't have to be perfect. You don't have to take out a straight edge. If you're using engineering paper, then you have lines on there, but draw it neat. Okay, so what is, after the table, we did the free body diagram. After the free body diagram, we're up to Edgar. What goes next, Edgar?
Now we've got to do the components.
The
of forces.
components. So take a look at all these forces. Are we very happy? I think so. Because all the forces are going in the X and Y direction, right? So there's no really components. Nothing's going off at an angle or anything. So does everybody understand that when I was doing my, when I was doing the interviews with you guys, a number of people were forgetting to do components before the equations. Why am I a stickler and wanting to see you do components first? Edgar.
So it's gonna reduce the amount of mistakes later on.
Yeah, you want to check it. Remember Isaac's little, what was that picture he gave
Chex
us?
Quest. We got to go on Chex Quest.
Chex Quest. There, he's smiling now. I see him. We got to check. But in this case, all the forces are in the directions are in the X and Y, so we have no components. Awesome. So then what's the next step, Edgar? After the components and the checks?
It will be now setting up the equations.
Equilibrium equations. Okay, you guys, sometimes you guys jump ahead. Great, but don't do it this time. Okay, We are not going to be like robots and say, some of the forces in the X equal this, some of the forces in Y equals this, some of the moments equal this. We're not going in that order. We are picking the easiest question, the easiest equation first to get us equations that have one unknown in it. So we are on Elizabeth. Elizabeth? Okay, Eric. Eric, are you here? Okay, Gerardo?
Hi.
So tell me what the 3 possible equations are for a 2D problem. I'm just gonna write them over to the right, and you don't even have to write them.
F of x equals 0. F of y
Sum of the
equals 0.
forces in the X equals
Yes.
0. What else?
Sum of the forces in the y equals 0.
Yeah,
And the moment about the z-axis is 0.
right. And it could be the moment about any point, right? Any point. But the maximum I have are 3 equations. Let me tell you that, you guys, I can do some of the moments about A equals 0, some of the moments about B equals 0, and some of the forces in the X equals 0. These could be my 3 equations. Is everybody hearing me? I don't have to do both force equations. I could do moment equations. It's just going to be redundant. When we introduce a 4th equation, it's just going to be a redundant thing, and you'll see it in a little bit. So Gerardo, thinking about the possible equations we have, and another thing I tend to do is I circle the things that are unknown. These are the ones I have to solve. So which equation do you want to do first that's going to be able to find one of the unknowns? I don't want an equation with more than one unknown in it. We're still up to Gerardo. What equation do you want to do first?
I'll do the moment about the a.
Great. Okay, let me say something else. Are force equations easier or moment equations easier? Everyone. Which one's easier? Force or moment equations?
Force.
Force. So let's first look at a force. Is there a force equation that could give me one unknown?
The forces on the X.
Yes, sum of the forces in the X equal AX plus 200 minus 300 equals 0. AX equals 100 pounds. Done. I did one equation. I did a force equation because they're easier than moments. And I got one unknown already. Okay, Gerardo, now I'm going to go to you. Now I'm going to go back. You had suggested another equation. What was that equation?
Moment about the a.
Good. Do some of the moments about A. Because some of the forces in the Y would give me 2 unknowns. So some of the moments about A. So NB times 2, positive, 300. This is where the couples would really be nice, right? But I'll do 300 times 2, negative, 200 times 2, negative, 100 times 7, 8, 9, negative. Let me just check. NB positive times 2, 300, 300 times 2, 200 times 2 negative, 100 times 9 negative. Okay, I'll wait for you guys now.
I have a setup question.
Yeah,
Earlier, we said that a 2D body can only give you 3 equations. But we
correct.
just identified more than 3
Well,
because of the different points.
Yes, but in the end, you're only going to be able to use 3 to solve them. We could use a 4th or a 5th for doing checks. But in a 2D problem, you will only be able to use 3 equations. You could choose whatever they are, whether they're forces or moments, but only 3 equations will give you answers. Because once you introduce a 4th equation, it's just going to be redundancy. It's like, you know how when you have 2 equations, 2 unknowns, you take one of the equations, you solve for the unknown, and then you plug it into the second equation. And in the end, you kind of come up with this blended equation. Whenever you pick an equation, more than 3 equations, you're really looking at a blended equation. It's hard to understand, but once you see, you'll see. Let's just keep going.
Okay, yeah, thanks.
Okay, so what is N? Did anybody get NB yet? 6, 4, 9. It's 19 divided by 2. Is it 1450? No.
950
950.
foot-pounds.
950?
Yeah,
Yes.
that's what I got.
Okay. And I'm up to Hyoji. Hyoji here?
Yes.
Okay, Hyoji, this is a normal, right? A normal we drew on the beam from the roller. If I got a negative for the normal, what would that, well, actually, let me go back to this first. Hyoji, if I got a negative for AX, what would that mean? If I got a negative value for AX, what would it mean about the direction of AX? You could pass if you want. I'm waiting on you. Okay, Isaac, if I got a negative for AX, what would that mean?
It would mean that AX was a compression force.
It goes the other way. Don't say
Yeah, it goes
compression,
the other-
just say it goes the other way.
way.
AX would go the other way. If I got a negative for this normal, what would that tell you?
That you made a mistake.
You made a mathematical mistake because a normal cannot be away from the body. Okay, we got AX, we got the normal of B. Jack, what third equation do you want to do? Because we just found AX and we found NB. What do you want to do?
AY.
Yeah, you want to find AY, and what equation would you like to use to find AY?
Sum of the forces in Y.
Great. It's always easy to do force equations. So that would be AY plus NB minus 100 equals 0. And AY is equal to, is it negative 850 newtons? Yeah. So
850
Jack,
pounds.
oh, thank you. Jack, the fact that I got a negative for AY, what does that mean about AY? Jack?
I'm not sure.
So you got, if you get a negative, we assumed a direction for AY, right? We really didn't know which way it went, but we got in, in the end, we chose it to go up, but we got a negative. So it means what, Jack?
We drew it the wrong direction.
Right, and don't say it, let's just say it goes the other way, because we don't want to make it sound like it was a bad thing. Because in this case, we have no idea which way it's going until we do the equilibrium equations. So we just put it in a certain direction and we get a negative and we know it goes the other way, right? Okay, so now, can anybody, where are we? Jason E. Jason Lavoy, Jason with an E, sorry. We found all three unknowns, but can you think of another equation we could do to check our answers?
To check that these are these values all work together is another way
Yeah,
to
or at least check some of them. Can we do another equation to check to see if they're right?
undoubtedly. It's not coming to me immediately.
Okay, so we certainly can't do any more force equations because there's only a sum of the forces in the X and a sum of forces in the Y. But we can do another moment equation.
We could do a moment about any point,
Any point.
and it would not necessarily. Are these all? I came in a little late. Are these all
That's okay.
couples?
No, we're looking at them as individual forces, but we
Okay.
could have.
So it wouldn't necessarily be the same value at any other location.
That's correct. That's a really good point, right? There are forces here that are not couples. So that means the moment about any point will be different. Good. So let's pick a point, Jason, where I could use all my unknowns. Is there a point I could use all my unknowns?
Because there would be a point where one or more of the forces go directly towards that point, and then you couldn't use it.
Yes, correct. So
Right.
let's say I picked this point right here. If I pick this point, AX goes right through it.
Right, exactly.
Right.
Or yeah, or B or something like that. So that wouldn't be
Or
useful.
B, right. B would, two of them would go through it. So let's pick another point.
Well, yeah. So not all the locations on this are labeled.
Right, so we'll label it. Pick a
Yeah, okay,
place
all
that
right.
you
So I
want.
mean, you know, where the 300 pounds is
Right.
is
Let's
applied,
do
like
that.
you could use that.
And let's just call that point C.
Mhm.
So Jason picked a point where all these forces create moments about that point. And now we're going to do some of the moments about C. So some of the moments about C, it's AY times 6 negative NB times 4 negative AX times 2 negative 200 times 4 negative and 100 times 3. Okay, I must have got something wrong. It's about C. So it's AY. Oh, I know why. Okay, AY is 6, correct, negative. NB is 4, negative. AX is 2, negative. 200 is 4, negative. 100, 3, negative. Equals 0. Do you see what I was concerned about? I have all these negatives, but look at AY, it's a negative value. So now I'm going to plug these in. So that's a negative 850 times 6 minus 4 times 950 minus 2 times 100 minus 800 minus 300 equals 0. And now I'm going to do it on my calculator.
Yeah, I was wondering about that AY because we determined it. We figured out that we had it drawn the wrong way.
Right.
So
You
would
guys,
we right hand rule it to say
what
you know, positive spin?
yeah, I'm hoping everybody's with me. So whenever I do some of the moments, I always still look at my free body diagram, and my free body diagram shows AY in this direction. So I still say AY is that way, it's creating a negative moment. But when I have the variable down here of AY, I have a negative 850. So I have a negative and a negative, and it gives me a positive. So 950 times 4 plus 200 plus 800 plus 300. Yep. Okay. What's your cat's name, Jason?
This is Rufus.
Rufus. Hi, Rufus. Okay, what questions do you have?
Wait, I have a question about the whole moments thing.
Yes.
You said earlier that there's different moments and different points in the system.
Okay.
But you're setting them all equal to 0.
Correct. So in the last chapter, we calculated what the moments are that are created due to each force, right? So we know the 200-pound force creates a moment. We know the 100-pound force creates a moment, and the 300. But now we are looking at, I'll answer your question a little bit, Gerardo, but we're now looking at a statics problem, right? Where this body has a connection at A and a connection at B. So if you go back to the initial problem, the 200, the 100, and the 300 are trying to make this T bracket spin. They're trying to make it spin this way. But this pin and this B have reactions at those supports. And those force reactions counteract the moment that these forces are creating. Even though a pin does not resist a moment and a roller does not resist a moment, their forces that are resisting are counteracting the other forces so that in the whole system together, there are no moments anymore. They all cancel out. Maria, thanks for asking for that question. So every force at a distance creates a moment. But these forces, these reactions at the supports, are creating an equal and opposite moment, that the whole system in the end is still and not moving. Maria, does that make sense?
Yeah, thanks. So we can, so in this, in every statics problem, then all of the sum of the moments equations, even no matter what point we pick, they're all going to equal 0.
That's correct. Because a static body, your table right now, is experiencing loads, but it is not moving sideways and it is not spinning, right? It's static. Even though if you, Maria, push really hard down on one corner of the table, maybe not too hard, hard enough for the normals to counteract it, it's not going to spin. But if you push down too far in a corner, your normals at the legs are not going to counteract it and your table is going to tip.
Okay.
But all our problems are static, so we are designing it so it doesn't move. Good?
Yes.
Okay, what other questions do you have?
You mentioned all forces at a distance cause a moment, but maybe that could be said that as long as there's a line of force, there's a distance between the line of force and the point. There's a moment.
Correct. Correct. So by saying all forces at a distance will create a moment about that point, as long as there's a distance, yes. Okay, so what did we do on this problem? We did the given and find like usual. We did the table like usual, except there's one thing different. Jason Lee, what did I add to this table that wasn't on our previous particle problems?
The moment is extra.
Right. In the first column, we're not just saying forces, but we're also putting moments. And in the next problem, you'll see there's a moment we have to put in the table. The number of knowns equals the amount of equations you need. What is the difference now, Jordan? With these problems where we're looking at rigid bodies, what's one thing different? In 2D bodies, how many equations can we have now?
3.
3. So in a 2D body, we could have 3 equations now. So in this particular problem, we had 3 unknowns. A 2D body, we only needed 1 body. Okay, Laura, next thing. What's the difference between this free body diagram and the statics of particles free body diagrams we used to draw? Laura? When we did a statics of particles, what was the free body diagram? What did it look like? Yeah, I can't hear you. But I think what you're saying with your hands is that you had one point and you had all these forces coming on that point, right? So in the statics of particles, the body you analyze was one point and all the forces went off or came to that point, right? Okay, well now we have the option of also doing rigid body free body diagrams now. And when you have rigid free body diagrams, then you have to make sure that you put the distances on. And
Gerardo's question in the
yeah,
chat.
I know, I realize I didn't answer it yet, but let me just finish this thought. And then you know what equations you have, pick the equation that has only one unknown first to solve the problem more efficiently. And in this particular problem, it was a 2D problem. We had 3 unknowns. We needed to do 3 equations. We solved it efficiently. And then in the end, we did another equation to check our work. And then you'll feel comfortable to give this homework or this design that you did as an engineer to your boss because you checked it already. Okay, Gerardo, your question was, let me see. I thought we took the absolute value of forces when solving for a moment. Yeah, we do. I guess I'm just not writing them anymore.
But
So-
how can we account for the fact that AY is negative?
Okay, so in this problem, I did some of the moments about A, I guess probably more the last one. The sum of the moments, this is absolute value of AY. Oh, I see. Oh, good question.
Yeah, it affects your right-hand rule direction.
Yeah, great question, Gerardo. Okay.
Given that, we almost should be redrawing it, yeah?
Yeah, but we don't want to do
Because
it.
if you're gonna,
Yeah, it's not the standard procedure. It's not the standard procedure, and it would be a waste of time. So, okay,
it just
so
seems like it'd be easy to mess up right-hand rule, yeah?
I didn't follow the question, but it sounds important.
I'm gonna explain it again. So Gerardo is saying that when you calculate moments, your moment is equal to the absolute value of the force times the absolute value of the perpendicular distance, right? So if AY, it's the moment about C due to AY is the absolute value of AY times the absolute value of the perpendicular distance. So he's wondering, why did I put a negative 850 into here when it's supposed to be absolute value? It's a great question. I've never had that question ever. 25 years. I don't know how to,
I think what you're actually doing is logically thinking about your right-hand rule setup. The negative sign means you know it's the other direction, so you have to logically flip it in your head.
Yeah. So I guess I don't know how to explain it, actually. I mean, I think what Dave said is fine. We determined, Gerardo, I guess the best explanation I could say is we determined this negative using the right-hand rule with AY going up. So AY is going up, put our fingers in the direction of force, I get a negative. But AY is actually going in the negative in the other direction. So either, I guess you could think the way Isaac thought and say, well, think of it as AY isn't going up, it's going down.
All right,
so do the right-hand rule with it going down. That's one way.
Is it because we assumed that it was going up, but we didn't?
Right, we assumed it's going up, and I'm doing the right-hand rule with it going up. But never, ever, ever, never, ever, ever cross this out and put it going down. You have to leave the free body diagram the way it was initially drawn because it goes with the negatives. So either you do the free body, you do the right-hand rule, and then remember, oh, AY is negative, it goes in the opposite direction. So then you would say, oh, it's actually a positive AY. Or for me, I just substitute in the value. And I kind of forget about that absolute value piece, but that might not be a good idea. It may be better to do this. So let's do this. The absolute value of the force is 850. The absolute value of the perpendicular distance is 6. And then say, oh yeah, there's a negative here. So when I do my right-hand rule and I get a negative, it's actually a positive. That's probably the better way of doing it.
I mean, Joanne, you could also say that, you know, like the way that you had it and just follow your free body diagram, know that it's going to be negative because of the way you have it. And literally when you're plugging in AY, you're plugging in a variable, not a value.
Okay.
You know what I mean? Like, does that, yeah.
Yeah, no, I think that's probably what I'm doing. That's what I do. I just plug in the number here, and I never even thought about that. I just always plug in the number. But let's move on. We only have 15 minutes left, and I want to do another problem. Okay. In any event, do it whatever way you want. But okay, so let's do the next problem. The next problem is this one here. So it says, a beam is loaded and supported as shown in the figure. The beam has a uniform cross section and a mass of 275 kilograms. Determine the reaction at point A. Okay, so let's do I'm going to put this down here and you could see it. Yes. So what's the first thing we want to do? So we're up to Liam. Liam, what's the first thing we want to do?
Given and find
Okay, so what's given,
the sketch info and
right?
the mass, which then you change to weight.
Great. So mass is equal to 275 kilograms. So the weight is 275 times G. So the weight, what does the weight turn out to be? 2695 newtons. Okay, and then the find, keep going. What about the find?
You would determine the reaction to support A, which would be, it would
Yes.
be
So
AX.
Can you see what it is?
Yeah, it's a fixed support.
Great, excellent. So what do I have here? And I'm going to use this as scrap. What do I have? What's the reaction support? Can it move horizontally? No, there's an AX. Can it move vertically? No. AY. Can I spin it? No, there's a moment. I think I'm just going to call it moment Z. Or maybe moment AZ. Let's call it moment AZ.
Yeah.
So, and Liam, you said that that's what they were trying to find. So, right. So AX, AY, and moment AZ. Good, Liam?
Yeah.
Okay. Luis, what do I do next? Luis? Okay, Mackenzie? Okay, Marcine.
We need the force and moment table.
Right. So force, moment, magnitude, direction. Okay, Marcine, keep telling me what to put in here.
You're gonna need your AY, your AX, and your MAZ.
Right. So here is a situation where there is a concentrated moment here at A, and I have to put it in the table. Do I know the magnitudes of those three?
No.
How about direction?
Yes.
Yes. And remember, the reason we're checking off that we know the direction is we know AY is in the Y direction. It's either up or down. I'm putting it in one way and we'll get a negative if we chose the wrong way. Okay, Marcine, what else do I have?
The 4,200 Newton meters.
Great. So we have this triangular load, right? And since I'm using scrap here, I could reduce this triangular load to one force, right? What do we want to call it? I guess usually I call it F. And what's the value, Marcine, of this? How do I calculate it?
Sorry, I'm blanking.
Oh, that's okay. So how do we calculate the load of a distributed load if it's triangular? Do you want to pass?
Don't we need to find, it's gonna go 2/3 in.
Right, it's going to go 2/3 in. Good. So I'm going to draw that here. And it's 2 meters in. But what's the value of this force? Do you remember? It's the integral. It's the area. Right. So 1/2. What's the base? 3. And the height is 420. Does everybody get that? The height right here, from here to here, is 4,200. And the height over here is 0. Right? The height. So 1/2, so that's half of this, it's 2,100. 2,100 times 3 would be 6,300, is that right? We're doing newtons. Let me look at my.
Yeah.
6,300.
That's correct.
Okay, so Marcine, instead of, I'm not going to write 4,200 here because that's not what the force is, right?
Yeah.
It was what the height of this distributed load is. So what is the force? We could call it F, or we could say 6,300 newtons. We know it. Anything else, Marcine?
No, I think that's it. Or do we need the weight?
Correct, the weight. And it's the weight of the beam the beam is homogeneous. So where is the weight of the beam going to be, Marcine?
The center.
Right. So here's weight. And do we know the value?
We know the mass, and then we can find the
Right,
weight
found
from
the
that.
value. Correct. And the direction?
Yeah.
Yes. Okay, so how many unknowns?
We have 3 unknowns.
Okay. How many equations do we need?
3 equations.
2D or 3D?
It's 2D. So
I have
we need one body.
one body. And what body do you want to analyze?
The whole beam.
That's right. We're analyzing the beam. So if you're drawing a beam, you're drawing a beam. You could draw a line. A line is fine, but remember to put the dimensions. Here's 3 meters, 3 meters. And now I have to put all the forces on, right? So I have AX, I have AY, I have my moment A in the Z, I have my weight, which is equal to 2695 newtons. Pen's running out. And I have this F load here of 6,300 newtons. I guess I have to do this in a different color. This is an external load here, and here's my weight. Okay, is there anything missing? There's 2 things missing that I see. Let's go to Maria. What's missing, Maria?
The axes?
Right? Say it positively.
The axes.
Great. One more thing. And the thing that you're going to leave out, you'll probably figure it out once you start doing moments, because the thing people typically leave out is a distance. What distance is missing, Maria?
The distance for the 6,300 newtons.
Right. So this distance right here is 2 meters, which means this is 1 meter. Okay, Matthew, after we do the free body diagram, what's the next step? Okay, Myra? What's the
Yes.
next? Say it again.
Start using or finding the equations.
Components, right? We do components first. After the free body diagram, we do components. However, and maybe Myra, you saw this, all the forces are in the X and Y. We don't need the components. They're already in their components. So then after that, Myra, what did you say we would do?
Use the equations.
Right. So which equation do you want to do first?
Some of the forces in the Y.
Yeah. Some of the forces in the Y. AY minus 2695 minus 6,300 equals 0. And AY turns out to be 8,9,8,9,9,5, and it's positive. Okay, Myra, keep going. What's another equation you want to do?
The moment at A.
Let's do an easier one.
Some of the forces in the X.
Yep. Some of the forces in the X equal AX equals 0. There's no other forces. And now we could do some of the moments about A. Okay, you guys. Well, let's do that, Myra. Miles?
Yeah.
Okay, great. Do some of the moments about A for me. It's W times what? Or let me put in the numbers.
Times 3.
2695 times 3 plus or minus?
Minus.
Minus. 6,300 times?
Times 5.
Plus or minus? Minus. Okay, you guys, this is going to be the weirdest thing in the world. And you have to listen to this because a third of you will get it wrong. When there is a concentrated moment, no matter where the concentrated moment is, you have to put it in every single moment equation. Why? You could think of it as a couple. There's a concentrated moment here. It's like a force going up and a force going down. And this thing, no matter where you put the concentrated moment, this whole beam is spinning. This beam is spinning. So you have to put, whether I did some of the moments at A or this point or any point in the system, I have to add in the concentrated moment. So it turns out to be 2695 times 3 plus 6300 times 5. And it comes out to be moment about AZ is 39585 Newton meters. And it came out to be positive. So this moment here is a concentrated moment, just like concentrated forces. Okay, is everybody with me for now? Look at me for a minute. When you do, look at me, when you do sum of the forces, you add every single force in, right? No matter where it is. When you do sum of the moments, you add in any moment that exists that is applied. Right? When you're trying to calculate a moment and there's a force at the point you're finding the moment, that force doesn't create a moment. But anytime you have a concentrated force anywhere in the system, you add it when you do sum of the forces. And that's the same with moments. When you have concentrated moments at any point, you have to add those moments into the moment equation.
Wait, if you were doing a moment about a different point, would you?
Yep,
So
let's do that because we still have to do a check, right? We're going to do a check. So Maria, where do you want to do a check? We already did the force equation, so we have to do a moment. Where do you want to do a sum of the moments about? Pick a point. How about the middle? It would be nice to like cancel a force.
yeah, I said the middle. Sorry, I was.
Oh,
muted.
great. So let's call that point B. So I'm doing sum of the moments about B. So it's AY times 3 negative. AX doesn't create a moment because it goes through B. Then there's 6,300 times 2 negative. And then you add in MAZ equals to 0. And
So-
why, Maria, am I adding in MAZ? Why am I not subtracting it?
Because it's gonna have. Otherwise, it would be. Otherwise, it wouldn't equal to 0.
That's not really the answer. The answer is I drew it positive.
Oh.
Just like when I draw a force positive, I put it plus. I drew the moment positive, right? So if I drew it positive, it's going to be added in. So let's see.
Can you scoot the paper over?
Say it again.
Scoot the paper over. You're off screen.
I can't even see where my screen is actually.
Start there.
Well, for you, it's right there. For me, I don't see me on this. Oh, there it
You
is.
just
Okay.
move the paper a little to the left.
Yeah, I
and
got it
align
now. Good. Okay.
Yeah.
So it's 3 times AY. So that's 8,995 times 3 minus.
And then I had a question. So
Yeah. Hang on a second.
Mhm.
Yeah, comes out to be 0. Okay. So to answer Maria's question, yes, no matter where I'm doing some of the moments, I have to put the concentrated moment in. Just like if I was doing some of the forces, I'd have to add the forces in. Okay, Jason.
yeah, so before when we were looking for a moment a location to check the sum of the moments. We picked one where none of the forces would cancel, and you made a different choice this time. I'm wondering what.
Right,
informed
good
that
question. So Jason, in this problem, I had, these were my three unknowns, right? I wanted to make sure I picked a point where those three unknowns were. And did we pick the 200 place?
What the question was, did we
Oh,
or
we
could
picked
we?
the 300, right? We picked this
Yeah, that's
location.
correct. We did.
We
pick
did
that.
this one because we wanted to make sure that all the unknowns were in the system, right? In this one, yeah, you're right. This equation doesn't have an AX in it, but there's nowhere on this body where AX doesn't cancel because it's a beam.
Well, in fact, it doesn't have weight either.
Right, but the weight we knew, that wasn't an unknown, right?
Okay.
Right,
Okay.
on this
Oh, I see.
problem, and this problem we picked where the 300 were because we were trying to check these three, right? So in a way, Jason, you're right, that this equation that we're using, we're really only checking AY in the moment. But I think I'm okay with that because it's very obvious to me that AX is 0, right? There's no other forces in the X. So I'm only getting to check AY in the moment.
Okay.
Okay, let's see if there's any other questions. Okay. Okay, and yeah, Luis said that he's with his kids right now, and Hyoji has Wi-Fi issues. So what other questions do you have about this problem now, or about the process?
I had a question.
Yeah, Angel.
Regarding, I don't know if it's too important, but
No, keep going. Yeah.
Your variable in the find table, or in your table of what you know and what you don't, your moment is marked as MZ.
Oh, this is very important. Boy, Angel, you should like take off 20 points for this. Look at this. Look at this shit. In the find, I called it MAX. In the table, I called it MZ. Oh, MAZ, Z. And here I called it MAZ. Come on. I'm supposed to be consistent.
Sloppy.
This is ridiculous. It makes it look like there's two variables. Thank you, Angel. Good. I should make a lot of errors and then have you catch them all. And I don't know if you've noticed, are you finding that you're making math errors when you do the problems? I mean, I am. I'm making math errors.
I catch them in my checks about
I'm catching them in the checks.
At least 1 out of 3 problems. Yeah.
Yeah, I mean, and stupid mistakes too. You know, add 2 negatives and get a positive or something like that. I mean, really stupid mistakes. But so that's why, you know, Rob and I and Karen, when she taught the class, and I think Carl taught statics before at Napa Valley, we're really highlighting the process so that you're proving to us that you know the statics part. And if you blow a math mistake, you're going to catch it at some point, you know? Okay, so basically now I'm gonna yeah, Marcine.
In the sum of the force of the moment about point A, why?
Okay, so the sum of the moments about point A, yes.
No, at the bottom of the page.
Oh, the sum of the moments about point A, yeah.
Why is it 3 for the perpendicular distance if AY is right on top of point A?
Okay, so sum of the moments about A, this is the weight. The weight is 3 meters away and it's negative.
Sorry, I thought that was AY. That's
yeah. Oh, yeah. No, they look, no. Okay, it's the weight.
Thank you.
Yeah. Okay, but the important things that stand out to me is know that this table has to be a force moment table now, right? And do the equations that have 1 unknowns in it first. And then always do a 4th equation for a check. On Thursday, we're going to be doing 3D problems, which are going to be more complicated. The process is going to be exactly the same. It's just going to be a lot more work because we have to do components and all that stuff. Okay, so I'd like to stop now. Let me share my screen for a minute. So I'm going to today's module, and here's an overview. It's a really short overview, but basically here are the steps. So I took the steps that we had before in solving particles problems, and I made it more complete. So this is the only steps you need now. You don't need the old steps anymore, because this steps include whether you're drawing it for a statics of a particle free body diagram or a rigid beam, a rigid structure. Okay. Then these are the problems that we worked on so far. We did these two, and we're going to do a 3D one, couple of 3D ones on Thursday. And they're all here. And then I'll put the Zoom recording, of course. You have two different homeworks, homework 19 and 20. 19 is 2D problems and 20 is 3D. Do you want me to post the solutions? I think the answer is yes. So I'm publishing the solutions. So now you have homework 19 and 19 solutions. I did not choose homework 20 yet, but I have until Thursday. And then today we're doing the quiz. Okay, and I have graded all the quizzes up till now, graded all the resubmitted quizzes. The only thing is I have 3 homework assignments I haven't graded yet. So I'm ready to give the quiz if you're ready. Okay, so it opens up. I guess I should maybe look at it. But you could open it up. Do you want me to? I'll open it up on my screen because I think that's helpful. My screen still being shared? You guys?
We
Doesn't look like
see the engineering paper program and we see your face.
Oh, okay, then it's not. Okay, hang on. I mean, you could open it up yourself, but basically we're looking at a cylinder here has a mass of 150 kilograms and it's supported by a two bar frame shown below. And you probably have seen this picture before too. I think it might have even been in one of your homeworks for the free body diagram homework. What I want you to draw is I want you to draw 4 free body diagrams. I want you to draw a free body diagram of a cylinder, a free body diagram of member AC, a free body diagram of member BC, and a free body diagram of the whole structure together. So you're just going to give me 4 free body diagrams. Remember, put in whatever information. I mean, they're a little shoddy on distances, so you may not have them. So then you can't put them in, but put in what you do have. Okay. And now just go for it.
No partial credit.
Well, I do that so people I give partial credit, you know.
Yeah, why does it say that?
Because maybe in the past I used to have a lot of whiners in class that would say, so then I said no partial credit.
All right.
So nobody could come and bother me. But you guys are redoing stuff, so.
Are points D and E on the cylinder, or are they on both? They're kind of at the edge.
Point D is at the, it's hard to see, but there's a dot. It's right where the interface where the cylinder is touching the bar, and E is where the cylinder is touching the bar.
Oh, okay. So that's the tangent points. Got it.
Yes, the tangent point. Great. Spoken like a good mathematician.
And when you say ignore the weight of the members, when you say members, you're only talking about the two bars, correct?
That's correct, because if you see the adjective on the bars, it says they're being called members,
Gotcha.
right? Member AC and member AD, I believe, or AB or something.
Awesome, thanks.
Hey, Joanne. You're muted, but when we're drawing the free body diagram, do we
Yeah.
just do it for, do we stop at point C, or do you want us to draw that whole bar up to like the end?
Oh, I'm sorry. Yes. You want to draw the whole bar. You
Okay.
guys, the whole bar. So I probably should have called it, I probably should have put another label on it.
Okay, thank you.
Yeah, the whole bar, not half the bar. You don't know how to do that yet, cutting bars. Thanks for asking.
We can cut bars.
Yeah, we will in a future class.
Thanks, Joanne.
Thanks. I'm looking through the free body diagram. I have a few people who have asked questions about some of the free body diagram homework, which was, I don't know what number, but it's the 30 problems that you had. You had to draw free body diagrams. And I'm hoping some people come to office hours today, if you're available from 1 to 2, because there's 5 of them well, 5 I'm seeing so far that people had questions on. So, okay, hope to see you then.
Yeah, have a good day.
Okay, bye.
Do you have a good trip?
Yeah, actually, I'm still there. I'll be here for 2 weeks.
Oh, how about that?
Yeah, we
Remote
just got
class.
COVID tested today to see if we're okay.
I hope it
Find
works out.
Yeah, I think so.
Okay, take it easy.
Yeah.
Joanne, when is this
Yeah.
quiz due officially? It's
I believe I decided at 10:30, so non-ASC is 11:15, and then I believe the ASC is until 12.
okay. All right.
But you'd have to check. I mean, I could check while you're doing the quiz. Why don't I check? I'll check.
Yeah, sure.
Yeah, 11:59.
Okay, great. Thanks.
Yeah.
Thanks, Joanne.
Yeah, you're welcome.
All right, thank you, Joanne.
Okay, see ya.
Thanks, Joanne.
Okay, bye. Oh, Amani, if you could
Yeah.
come to office hours today, I just looked at all those problems and I could explain that free body diagram problem to you.
Okay. Yeah, I can.
Okay, great. See you then.
See ya.
Okay.
Thank you, Joanne. Have a good day.
Okay, see, I hope to see you later.
Have a good day, Joanne.
Okay, see you later. Okay, bye.
Thanks, Joanne.
Okay, see you later. Hey, Jason, you doing okay?
Yes, thank you for checking in. I got a phone call that's completely irrelevant to this, but very
Oh,
important. I'm
okay.
just-
I'm thinking maybe you're the only one left, although my screen's still, can I stop sharing?
Yeah, you can stop sharing.
Okay.
Oh, wait,
And then-
Can you actually share for one more second? I'll take a screenshot, actually, is what I'll do.
Sure. Hang on a sec. Okay, yeah, take a screenshot.
Done, thank you.
Got it? Okay, I'm gonna leave, okay?
Alrighty.
All right, maybe I'll see you later. Good luck.
Yeah, bye.
Bye.